Kia ora, Year 12 and 13. This is a really lovely question from the 2006 Scholarship Calculus paper. It's got a little bit of trig and then a whole bunch of complex numbers. It's also got tons of building blocks. So I think I'm going to split this video into two, and I'm going to do the trig part and a wee bit of other useful stuff, and then come back in a second part to the complex numbers bit. So the first part is this: show that cos of pi on 8 can be written exactly as this thing here. And then we're going to solve somehow that's going to link up to this equation here. And we have to again give exact solutions. So on the next slide, I've written down a list of building blocks that are going to help us with that whole question. And here they are. So the first thing is the double angle formula for cosine, right? And you should be able to spot that as soon as you see that pi on 8. And that comes back to knowing your special triangles inside out. So if you're wobbly on special triangles, you need to make sure you're not. So draw them out, put them up on the fridge, put them somewhere where you're going to see them all the time, because they come up all the time. The next thing is the idea of an even and odd function. That comes up quite late in the problem. How to divide complex numbers is important. We're also going to use de Moivre's theorem. And the kind of weird thing that really helps in this question is Pythagoras. And Pythagoras linked in with the trig identity. So if we go back to it now, the thing I'm going to do first is to use the double angle identity to solve the first part of the problem. But the next thing I'm going to do that's not explicitly in the question is I'm also going to find an expression for sine pi on 8. So just to add that into your notes, what is sine pi on 8? Because I'm going to use that later on in the complex numbers part of the problem. And you can probably guess where. When we've got complex numbers, we can either write them in rectangular form as z equals a plus bi, or we can write them in polar form, which is r cis theta, or r cos theta plus I sine theta. And in the second part of this problem, we're going to use this cos of pi on 8, but we're also going to need sine of pi on 8. So let's do the trig part now. So the double angle formula is this: cos of 2 theta is equal to 2 cos squared theta minus 1. So here we're going to have theta is pi on 8, 2 theta is equal to pi on 4. That helps me because I know that cos of pi on 4 is 1 on root 2. So cos of pi on 4 is equal to 2 cos squared pi on 8 minus 1. Bringing across, adding to both sides 1, so I get 1 plus 1 on root 2 is equal to 2 cos squared pi on 8 root 2 plus 1 over root 2 is equal to this. Now, it's worth keeping an eye on where I'm trying to get to. I want to show that it equals this in the end. And you can see that I've got a 2 in the denominator, so no surds in the denominator. So it doesn't really matter when you do this, but we're going to rationalize the denominator. I might as well do it now. So that means I'm going to multiply numerator and denominator by root 2. So as I said, you could leave that till later. Expanding out the top line gives me 2 plus root 2 divided by 2. So now we have 2 plus root 2 on 4 is equal to cos squared of pi on 8. Okay, so just be a little bit careful here. I don't think they were in the schedule, but they should have been. Well, I shouldn't really tell scholarship markers what to do, but what we've got to think about is that if I just have, say I had 9 equals x squared, there are two solutions to that, right? X can be plus or minus 3. So how do we know here that we don't have to worry about the negative solution? Well, it's because cos of pi on 8 is in the first quadrant. So if I think about pi on 8 here, cos theta is equal to the x component over the radius, right? And so we know that cos of pi on 8 must be positive, so we ignore the negative solution, and we just take the square root of both sides. So we get cos of pi on 8 is equal to the square root of this, which is this, as required. Okay, the last step we're going to do is we're going to somehow figure out what is sine of pi on 8. And this is where Pythagoras comes in. We can think about cos of pi on 8 as going all the way back to year 9 or 10 trig, probably year 10. This is the adjacent over the hypotenuse. So we can draw a triangle that's got those side lengths. This is the hypotenuse, and this is the adjacent. And that will let me work out what sine is. Okay, so there's pi on 8. And the hypotenuse is 2. And the adjacent side, this one here, is 2 plus root 2. So if I ever need to get a sine from a cosine in a problem like this, this is usually a good way to start. So what's this side? Well, by Pythagoras, we've got a squared plus, we'll call this b squared is equal to 2 squared. 2 plus root 2 plus b squared is equal to 4. B squared is 2 minus root 2, giving me b as the square root of this. So we can draw that back on our triangle now. There's pi on 8. And here's 2 minus root 2, and this side is 2. And that means that we can now find all of our trig ratios if we want to. So we'll just do sine, but we could do tan and we could do the reciprocals as well. So sine of pi on 8 will be root 2, the square root of 2 minus root 2 on 2. Okay, so I think that's enough for one video because that's already 7.5 very long minutes of your life that you'll never get back. Have a go at the complex numbers part, and I'll come back and work through that using these results later on this morning. Thanks for watching.